This conference will now be recorded.
Very good evening, students. Today we'll be starting a new chapter and we'll be learning very interesting things in electromagnetic induction chapter. So, what is electromagnetic induction? First of all, see, we have seen in the previous chapter what we have seen. We have seen that if you have a conducting wire which is carrying current I, we have seen that produces a magnetic field around it. So this is seen in like proved in Oersted's experiment, right? Oersted's experiment. Okay. So again, we have seen if you have a current carrying loop, it produces a magnetic field, and we have found out magnetic field at any point on the axis of the loop, right? So we could see that electric current produces magnetic field. So this was actually in 19th century. This was a really tremendous discovery that see electric current produces a magnetic field. So that is actually called electromagnetism. So the physics where like the branch of physics where we discuss electric field and magnetic field, correlation between electric field and magnetic field, that is actually electromagnetism. Correlation between electricity and magnetism, that is electromagnetic, like electromagnet, or sorry, electromagnetism, that is called electromagnetism. Now we are seeing electromagnetic induction. You know, you might be thinking that see, interrelation means what? I have electric field and separately I have magnetic field as well. So is it possible somehow that electric field can produce magnetic field, or is it possible somehow magnetic field can produce electric field? Okay, so this is the reverse effect. So direct effect we have already seen, that electric current, that means electric field. Electric current means electric field. There is electric field. So electric field is producing magnetic field. Okay, we have seen this in Oersted experiment. When a current is set in a conducting wire or a loop of conducting wire, we see there is magnetic field. So there we can say that electric field is actually producing magnetic field. Is it seen that there is a reverse effect? What is reverse effect? Reverse effect of electromagnetism. That means somehow magnetic field has to produce electric field. So is it seen somewhere? Answer is yes. So this was discovered by or observed by Michael Faraday, Joseph Henry, etc. So Joseph Henry, and many other scientists later. Okay, they have proved that there is a reverse effect. So this is actually the beauty of electromagnetic induction. Like here, see, here is the necessity of electromagnetic induction when you want to produce electric field from the magnetic field. Okay, so what is this electromagnetic induction phenomena? The phenomena like phenomenon in which an induced EMF, hence an induced current, is generated by a time varying magnetic flux linked with a closed circuit is called electromagnetic induction. So it is actually the phenomenon in which an induced EMF is generated by a time varying magnetic flux. We'll learn that. We'll see what is exactly this equation that was given by Michael Faraday. We'll see that magnetic flux. So we see that time varying magnetic flux linked with the closed circuit is generating electromagnetic induction, like producing EMF, which is actually electromagnetic induction. I'll make you clear once again because this is important to understand. This is a phenomenon in which induced EMF will be produced from where? From time varying magnetic flux. Time varying magnetic flux. So we see in this induction chapter we'll see how magnetic field will produce electric field. This is the reverse effect. Okay, so magnetism, electromagnetism, what is the forward effect or direct effect? Direct effect is that electric current produce magnetic field, but what is the converse effect? Whether magnetic field can produce electric field also. So this is actually converse or reverse effect. So this reverse effect is actually electromagnetic induction. But how the electric field? Now we'll see how this EMF, induced EMF, is produced by magnetic field, time varying magnetic field. Here it is said time varying magnetic flux link. See, if I have a loop, then magnetic flux, we have to talk about magnetic flux. Okay, we'll just discuss now what is magnetic flux. Now we'll see what is magnetic flux. Magnetic flux through any surface placed in magnetic field is defined as the number of magnetic field lines crossing the surface normally. So this is as simple as this. See, I have a surface. Here it is obviously a plane surface, but for any surface it is true. When, see, these are the magnetic field lines. Okay, magnetic field lines. Magnetic field lines. This magnetic field line, when passes through, magnetic field lines pass through an area perpendicular to the area, then it is actually, it is said that there is a flux linked with that particular surface or with that particular loop. If suppose this is a rectangular loop, or if I take a circular loop kind of this, so I have a wire of loop like this. Okay, sorry, loop of wire like this. So if the field lines, magnetic field lines passes through it like this, normally passes through normally, okay, passes through this circular loop, normal to the area of this loop, normal to the area of this loop, then it is called that the loop is actually linked with flux. Okay, the loop is linked with flux. In very simple language, number of field lines, magnetic field lines crossing perpendicular to the to a particular surface is called actually magnetic flux. Now see, magnetic flux, it is, we have seen the definition analytically or verbally. Now somebody may ask, can you give me some mathematical formula for flux? Answer is yes, we can give it. See, the magnetic flux is numerically defined as, so it is, first of all, it is denoted by phi. Magnetic flux is denoted by phi. It is actually the product of, it is the product of magnetic flux and the area. Okay, but here one thing you have to understand, not only this, I have to take care of. So if I take a vector product, sorry, this is a dot product, then b dot a. So this gives actually ba cos theta. What does this mean? Ba cos theta, where, what about this cos theta? So it is product of, see, b cos theta, I'll write b cos theta into a. It is the product of the component of the magnetic field along the direction of the area, and product, see, and area also has to be multiplied. So how do we find out flux mathematically? It is the product of magnetic field, component magnetic field along the direction of the area and the magnitude of the area. So this is magnitude of the area. So in general, see, this is the point. In general, this is actually ba cos theta. So this is actually the magnetic flux expression, mathematical expression for the magnetic flux. Now this flux, see, suppose I have magnetic field lines at some places which are, see, parallel to the horizontal plane. Okay, now if I have my surface through which the magnetic flux may pass, okay, if I take that area just perpendicular to this, so this will give some amount of flux. But if I keep this same area somewhat tilted, since it is, see, this theta thing is there, so this theta is the angle between the area normal and the magnetic field. See, this is clearly given here. Is the area, like an n cap is the area normal, and this is the magnetic field. Okay, magnetic field, the angle between the area normal or direction of the area and the magnetic field is theta. So we can see the flux can be mathematically defined as the component, product of the component of magnetic field or magnetic induction along the direction of the area of a particular shape and the magnitude of the area. Now see, because of this, see, we have got now expression for the magnetic flux, see, ba cos theta. So where that will be maximum? It will be maximum when theta is equal to 0 degree. Theta is equal to 0 degree. So theta will be 0 degree, then phi will be phi max. Okay. This is the magnetic flux, sorry, maximum flux passes through an area. Okay. When theta is 0, that is the maximum flux. When, see, this is the situation, this is actually maximum flux. 0 flux when, see, this cos theta, theta is 90 degree. That means this is your magnetic flux density and area normal is like this. See, this is the figure. This is the n cap. The angle between the area normal and the magnetic field is theta. So this theta variation, with the variation of this theta, there will be various values of, like, or different values of flask, magnetic flask. So magnetic flask will be maximum when theta is equal to 0 degree. Okay, and the magnetic flux will be 0 when this is on the flat, so B is on the flat plane itself, and then this is the normal area normal. This is 90 degree. Now see, I have learned. See, I'll just erase this point. I have learned that magnetic flux phi can be written as BA cos of theta or B cos theta. Okay. Now, if the area is not very uniform, like this, you see here, the area, if the area is not very uniform, or it doesn't, if it doesn't have any physical symmetry, then what we should do to calculate the flux, we have to actually break into small area. Okay, we have to take small area element and then calculate the flux for each. Suppose for the shown one, this is the ds. Okay, so ds has direction n cap. Then this will be b. So we have to first of all find out ds. So we have to do b dot n cap ds. This is actually flux integrating over the whole surface area. Okay, so this is another form of calculating flux. Okay, so we have seen general formula for d phi. Okay, phi itself, phi b dot n cap ds phi equal to phi. Now we'll see What about now, madam? Is it there now? Okay, then I think I'll just I had started already 15-20 minutes before. Shall I repeat the class? I'll just re-record from the beginning then.
This conference will now be recorded.
Good evening, dear students. Today we are starting a new chapter, electromagnetic induction. So here we have in the previous chapter we have already seen that electric current produces magnetic field around it. Okay, so electric field can produce magnetic field. So this is actually electromagnetism. That means there is a correlation between electricity and magnetism. That is electromagnetism. But today we'll see the reverse effect. That means magnetic field also can produce electric field. In the previous chapter we have seen in the electromagnetism, electric current or electric field produces magnetic field. Today we'll see magnetic field also will produce electric field, which is the reverse effect. This reverse effect is actually electromagnetic induction. Okay, let us see. So this was actually observed by Oersted, right? Current produces a magnetic field, was first proved experimentally by Oersted. Then Ampere and other scientists had come to prove the same thing, that current can produce magnetic field. In 19th century, we see another group of scientists like Henry, Michael Faraday, Joseph Henry. They could just like discover the reverse effect of this electromagnetism. So what is electromagnetic induction? The phenomenon in which an induced EMF is generated by a time varying magnetic flux linked with a closed circuit is called electromagnetic induction. This particular sentence may not be very much understandable because we may not know what is magnetic flux. We have learned a little bit about magnetic flux in the previous chapter, but let me first discuss here what is magnetic flux. We have already learned electric flux in Gauss's law, right? While calculating electric field using Gauss's law, right? So here we have to first learn what is magnetic flux. Okay, all right, we'll see here what is magnetic flux. See, if I have a loop of some conducting wire, and suppose there is a source of magnetic field where the magnetic field lines are passing like this, passing through this circular loop. Actually, magnetic flux is the number of magnetic field lines passing through the loop area. But how it passes? Field lines should pass normally to the area of the loop, normally or perpendicular to the loop area of the loop. So magnetic flux through any surface placed in a magnetic field is defined as the number of magnetic field line crossing the surface normally. So this is actually magnetic flux. I'll repeat it. If I have a loop like this, and if field lines are passing normal to the area of this loop, then we'll say the loop or this loop of the wire or coil of the wire has linked with some flask. Okay, See, if I say water flask, what do you mean by water flask? That means in a tube. See, this is actually a tube, water tube or water line. If I draw a cross section normal to the length of this tube, okay, water flask means what? The amount of water which is passing through this particular cross section in unit time and normal to this cross section. So that is actually this is amount of water. Okay, water flask means amount of water which is passing through a particular cross section normal to the cross section. So that particular amount is called actually water flask. So similar to that is here magnetic flask. Obviously we have discussed this flask in the previous chapter, in the first chapter itself, electric flask. Okay, so but how do you mathematically define magnetic flask? Anyway, it is actually denoted by phi. Flask is denoted by phi. Okay, sometime in some books it will be given phi b. That means phi e also will be there. Phi e means flask in electric field. Okay, flask of electric field or electric flask, phi e, and phi b means magnetic flask. Okay, phi b means magnetic flask. And this magnetic flask is actually numerically defined as the product of the component of the magnetic field along the direction of the area of the loop and the magnitude of the area of the loop. Just take this particular case. See, I have an arbitrary surface area, okay, of this particular loop. Now magnetic field lines are in the horizontal direction, they are parallel, so this is uniform magnetic field as the field lines are equidistant from each other. Now this is a particular, this is small element of area, small area element which has its direction normal to this area, right? See, if I have an area, so this is actually, this is normal, area normal, this is perpendicular to the surface. Okay, and this, you know, this normal can be inward and outward. In general, for open surface, the normal can be taken. Suppose I have a sheet of paper, I have a sheet of paper, I can take the normal to that sheet of paper either in the rightward direction or in the leftward direction. So for the case of open surfaces, this is not mattering much about the direction of the normal, area normal. So now we were discussing what is the expression. So we have to actually take the component of this B. So component of this magnetic field along this will be B cos theta. Okay, as this n cap, the area normal, is making an angle theta with the magnetic field, then B cos theta is the component of the magnetic field along the direction of the area normal. Okay, and I have to multiply with this what? So B cos theta is the component of the magnetic field along the direction of the area and magnitude of the area A. So this is actually the expression for the magnetic flask, BA cos theta. So this BA cos theta, see, vectorially it can be written as B dot A cap. Sorry, B dot A cap. Okay, B cap dot A cap. I mean to say this is B vector, A vector. Okay, so dot product will give you cos theta, right? Better not to give cap. You might be thinking that these are unit vectors. No. B is the magnetic field. This A is the area. All right. So we can see the flask depends on the angle between the magnetic field and the area normal. See, this is the angle. This is the area normal or direction of the area for this particular small element of the area. And this is the magnetic field. So theta is always this. So that is the angle between the area normal and the magnetic field. And the amount of flask which passes through a particular surface area depends on that particular angle theta. So b cos theta. So phi will be maximum. Phi will be maximum if this particular term is maximum. Cos theta is maximum. So when is cos theta maximum? When theta is 0, right? So phi will be phi max when theta is 0. So what do you mean by theta is 0? So theta 0 means when? So when the area normal is along this way itself, along the direction of magnetic field, then it is called, then the angle between them is 0 degree. Okay, so look the first situation. So here, look this first situation here, the direction of the normal, area normal. See this for this particular vertical plane. You can see this is the area normal and this is the magnetic field lines. So there is no angular differences. So theta is 0 degree. So there the flask will be maximum. Phi will be phi max. So phi will be phi max at theta will be at theta is equal to 0 or 2 pi whatever. But see this case here theta is 90 degree. Here theta is 90 degree. So 90 degree means what? Flask is 0. So when the angle is 90 degree, then that means if your field lines are parallel to the or tangential to the surface, then there will be no flux passing through that particular surface. Okay, so these are few points I need to tell you here. I'll now show you here. In general, I have written b cos theta a, or if suppose the area through which the magnetic field lines passes is not very uniform. Okay, if that is not uniform, then I cannot write just b a cos theta. I cannot write. In that case, you have to take small area element like this I have shown here, and then you have to find out what is the flux for this particular element d phi. That is actually b is constant in here. I'm taking, so b cos theta. You can write b cos theta into ds. Okay, in vector term, like, okay, vector deal, you can write b vector dot n cap ds. Okay, or directly, sorry, b dot ds, b dot ds, b dot ds, like this. Now total flux passing through the whole area will be integration over the whole area into b. Okay, so this is actually formula for any arbitrary surface, b dot n cap ds. This was being done in case of electric field also. All right. Now we'll see what is the dimension. I'll just go to the next page maybe. Okay. Before I discuss the unit, I'll write here dimension. Dimension of flask will be CB. Dimension of any cos theta doesn't have any dimension. Dimension of B means magnetic field and A means area. So magnetic field, dimension of magnetic field, how do you get? I know magnetic force AB, QVB. Right from here, I'll write. Okay, so F is ml to the power minus 2. ml to the power minus 2. F ml to the power minus 2 divided by A into T. That is the dimension of current, and then you have again L to the power minus 1. L to the power minus 1 for the velocity. So overall, what we will get this dimension m this is L to the power minus 1, this to the power minus 2 and A to the power minus 1. Let me cross check. This m to the power minus 2 m to the power minus 2 A to the power minus, I'm sorry, this A is this, and there will be another A here, L square. There will be L square as well. Okay, so this is actually the dimension. Dimension of the magnetic field. So m to the power minus 2, L to the power minus, sorry, L square and A to the power minus 1. Okay, so now we'll learn about the unit. Okay, just let me just confirm you about the dimension and this first. Just a minute. Okay, so this is m to the plus 2. This one. Okay. Okay, now see, it has two different units in two different systems. So Weber is SI unit for class. So see class sometimes so B into A is plus, B is plus, right? It is called magnetic in that magnetic density. So this is actually, it is called magnetic flux density also. Phi by A, magnetic flux density also. So unit SI unit of magnetic flux is Weber, and it is denoted as flux produced in a flux produced when a uniform magnetic field of 1 Tesla act normally on an area of 1 meter square. So this is 1 Weber means Tesla into meter square. Tesla into meter square, and in physics it is named as Maxwell. So 1 Maxwell is equal to 1 Weber is equal to 10 to the power 8 Maxwell. Okay, so 1 Weber is equal to 10 to the power 8 Maxwell. Now we learn the main part here, that is electromagnetic induction, which was actually like how it was discovered. Electromagnetic induction, how was that discovered? And see, Michael Faraday and Henry, they independently carried out few experiments, and from the observation of the experiment, Faraday has given a law that is called Faraday's law of induction. Okay, so see, Michael Faraday and Henry had taken a loop C1 say, and a galvanometer is connected at the two ends of this coil, and they had taken a bar magnet, and see, as the arrow says, the north pole is being taken towards the coil. Okay, so this is actually, see, the experiment is induced EMF produced by relative motion between coil and the bar magnet. So Michael Faraday just noticed that when the north pole of the bar magnet is taken towards the coil, there is a deflection in the galvanometer coil, okay, attached to this particular coil. That means what? There is a presence of current in the circuit. If the galvanometer pointer deflects, then it indicates that there is a current or there is a flow of charges. There is a flow of charges. Again, they have seen that when the north pole is taken away from the loop, then also there is a deflection, but now this time the deflection is in the opposite direction. Okay, deflection of the galvanometer pointer is in the opposite direction. Further, if we change the speed, okay, that means the deflection is faster if we move the bar magnet faster. Okay, if the bar magnet is moving faster towards or away from the coil 1, then the deflection in the point of the galvanometer is also becoming faster. Okay, so this was first observation. There was another observation that if we just keep this bar magnet held fixed, if the bar magnet is held fixed and the coil is moving towards the bar magnet or away from the bar magnet, then also we'll see there is deflection in the galvanometer coil. That means what? There is a flow of charges. So these were a few observations from the past experiment that one can conclude that induced EMF may be produced due to relative motion between. Oh, one more point I just wanted to tell you, that if there is no relative motion, there is no current or deflection in the galvanometer coil. Okay, so let us see the second experiment by Faraday. In the second experiment, see, we have already learned in the previous class that if I have a current carrying wire and a loop is made out of it, and if current is flowing through it, you know, it will produce a magnetic field. And in fact, this coil will itself act as coil itself will act as a bar magnet. You know that bar magnet, because you know, if we use the thumb rule, then we'll see this side will be north, this side will be south. So each loop or each coil of wire can act as a bar magnet. Yeah, so because it acts as a dipole. All right, so in this excuse me, in the second experiment, Michael Faraday had just replaced the bar magnet with the second coil, and you have to understand here how the second coil was. See, second coil it will produce magnetic field, or it will act as a bar magnet only when current will be produced, current will be flowing through the coil. Okay, so that's why, see, the second coil C2 is actually connected with the battery so that it can give a current. All right, now what were the observations with this particular experiment? Here also the conclusion was that so here first the coil 1 was held fixed, okay, and the terminals of the coil 1 was connected to the galvanometer. Then when it is fixed, like it is held fixed, now second coil is actually carrying a current, some current. So this second coil is producing current, and you know, okay, so let me just first discuss about the observation itself. The first coil was held fixed, then second coil, there was a battery, so current was flowing through the battery. Okay, so the C2, when C2 is actually brought near to the C1 or taken away, then also we see there is a presence of flow of charges and presence of current in the coil C1. Obviously, while taking towards the coil C1, then galvanometer gives the greater deflection. If it is taken, say C2 is taken away from the C1, then the galvanometric deflection will be a little bit less. Okay. Now, if this is fixed, but this is now C1. While C1 is actually moved to and fro of this coil C2, then we say there is a magnetic field. I'm sorry, there is a deflection in the galvanometric coil. So either of this is in motion when there is a, I mean to say that when there is a relative motion. So actually I am writing where there is, let us say when there is a relative motion. So when there is a relative motion, due to the relative motion, this maybe the current is seen in case of second, but in the second coil. So this was actually the observation when there is a relative motion between the coil, then okay, so I'm just erasing this. When there is relative motion, then only current is flowing in the circuit. Okay, I'll just discuss this third one. See, this itself was made a little bit modification with the key. So in the third experiment, what was done in this C2 coil, there was a plugging key given which was acting as switch. Now when the see, now he just wanted to confirm whether the relative motion is at all required for producing current in the other coil. The answer is no, which will be proved from here. See, there was a plugging key here, or switch, tapping switch. Say it was, when it was suddenly tapped, there was a deflection in the galvanometric coil. But if this tapping switch is tapped for a long time, there is no deflection in the second coil. Okay. Whereas when the tapping switch is just off, suddenly made off, then also there will be a deflection. Okay, that means there is a current flow, or there is a production of EMF or current, not only due to the relative motion, but it depends. So there was a little modification, as I said. Okay, anyway. So what was the conclusion from here? That the relative motion between two coils, or relative motion for getting electric current, is not So there was some other reason for galvanometer wanted to deflect. Okay, all right. Now see why. Well, let us discuss why, or let us discuss the result we have seen. I'm sorry. So what were the conclusion? I'll just write from the experiment. What were the conclusions? So overall conclusion was that the magnetic field lines when passes through coil, then it is said that there is a flux link. Okay, flux is B A cos of theta. Now when the coils are or coil or permagnet is brought near and taken away from the coil, then what happens? The number of field lines which are passing through this coil will be less. That means flux link with the coil will be decreasing when we go away. So this is actually the variation of the flux. Okay, variation of the magnetic flux link with the coil is the original reason for the current or current induced in the other coil. So this was the conclusion. So I think I'll stop it here for today. In the next class, what I'll do in the next class, I'll take up the detailed conclusion of this Faraday's experiment, and then I'll continue. Okay. So thank you for your patience. Bye for today.